Hey, Algebra 2 Honors students, this is the beginning of Unit 18 on statistics. Statistics will be broken up actually into two parts. So we're going to have a quiz halfway through, and then we'll have another quiz when we finish up the rest of the unit. One thing to kind of pay attention to is that in the blank copies that are posted on my website, you can actually ignore the day 0 that was to start the blank copies there. We're just going to get started right away with day 1. Who needs day 0 anyway? That's silly. So we're going to talk about something right away called the normal distribution. Now, as far as statistics go, you learn about statistics in Algebra 1. So a lot of the terms that I use today, I think you'll be fairly familiar with. If there's something that you're not familiar with and it doesn't make sense in context as I'm going over it, or if it goes too fast, I will count on you to email me, ask it in a Google Meet next week, and I will definitely clarify that for you. But what does a normal distribution look like? Well, at the start of the notes, you see two different histograms. And I'll tell you the one on the left and is an example of a normal distribution. And I think you probably would have guessed that had I had you, make a quick guess as to which one's normal and which one's not. The one on the right is considered actually to be skewed to the right, which is a little counterintuitive because actually most of the data is kind of grouped on the left-hand side. And then you can see how it kind of slopes down to the right-hand side. But if it was mostly grouped on the right-hand side and sloped down to the left, then we would say it would be skewed left. So what are some of the characteristics of a normal distribution? So for normal distributions, one thing that we should know is that it should have its peak at the center. Okay, so the center of this distribution probably is right about here, so that's not the peak. But this distribution definitely is reaching its peak at the center there. And what we know in normal distributions is that the mean, the median, and the mode should all be the same. So as a quick reminder, mean is the average of the data that you're looking at, median's the number in the middle, and then the mode would be the number that occurs the most. So these are definitely some good characteristics to note about what are called normal distributions. We're going to see a nice symmetric distribution if it's a normal distribution. So it doesn't have to be perfect. Notice how this one I'm classifying it as being normal, but it's not equally spaced on both sides, but it's pretty close to that. And then finally, you can see those curves drawn over the top. So you're going to see that a good way to model normal distributions is by using a bell-shaped curve. And in fact, the area underneath this curve is going to become pretty important to us in our study of statistics. And you'll see how it actually relates to what we've been doing in the last unit with probability. So there's a histogram below that shows a distribution for the heights of 1,000 women. And you can see the heights in inches are plotted on the x-axis. And then these are relative frequencies of each of those heights. So you can see, like kind of in the middle of our distribution here, that about 14, 15-ish% of the 1,000 women fell into that height range. So if you were to classify this, looking at the two classifications at the top, I would hope that you would say that this appears to have a nice bell-shaped curve to it. So this is a normal distribution. So it says the mean of the distribution of women's heights is 64.6, and the standard deviation is 2.75. Interpret each in these contexts. So we've already talked about how mean is just going to be the average height of the women in this group, but we'll have to talk a little bit more about what standard deviation means. And I believe that you talked about standard deviation in your Algebra 1 courses. So the 64.6 is the average height in inches of the 1,000 women whose data was collected here. Okay. So when we talk about standard deviation, which will be a huge part of what we talk about in the next few lessons here, the standard deviation's definition is it's the average distance that values vary from the mean by. So the way we would interpret the 2.75 is we would say 2.75 inches is, I called it the typical or the average number of inches that a woman's height is from the mean. Okay, so on average, a woman would be about 2.75 inches taller than 64.6 or 2.75 inches shorter than the average height there. Okay. So some quick discussions about mean, standard deviation. We're going to see how we can use normal distributions and some of this information to make other conclusions in just a moment here. So on the next page, I'm going to have you hit pause about distribution shapes at the top. See if you can classify those distributions. You know some of the terms, such as normal, skewed left, and skewed right. I'll tell you the first one is not an example of any of those three. See if you can think you can come up with a name for those, but the others I think will be pretty straightforward. Okay, so hit pause because I'm about to reveal the answers here for those 6. Okay, across the top row. We actually call that first graph a uniform distribution. Okay, since all of our data occurred, no matter what this is, right? If we look at the last example where it was heights, and the number of people who had those heights, okay, you know, if there's an equal number in each of those groups along the x-axis, then we call that a uniform distribution. This is looking extremely normal in the middle. This is skewed right. And at the bottom, we have those 2 others. And those would both be normal. Okay, even though it's kind of like shifted over on the x-axis here, you can fit a really nice bell curve over the top of this distribution. So that we would definitely consider to be normal. So something that's pretty important in the study of statistics would be something called z-scores. If you take a look, it says when a distribution is normal, we can use z-scores to standardize any set of data. And that word standardize is pretty important in terms of, you know, you've heard of standardized tests and things like that. So z-scores are a helpful way to compare people within a given set of data. So the z-score, what does it really represent? It represents the number of standard deviations, which we just talked about that a second ago, that somebody is away from the mean. And any normally distributed set of data can yield a z-score. Here's going to be in this box a formula for how we will calculate z-scores in this lesson. So z-scores can be calculated by taking an observed value, subtract the mean from that, and then divide that result by the standard deviation for that set of data. So if we think about, you know, the women's heights that we had a second ago, we knew the mean for that set of data. We knew the standard deviation. So if we had observed a particular person to have a certain height in that group, we can calculate a z-score for that person, and then we can use that as a method of comparison. If your z-score is 0, I think this will make sense. If z equals 0, that means it's the same as the mean because the numerator would become 0 up there. The observed and the mean are the same. So then what does it mean if we have positive and negative z-scores? Positive z-score would mean that somebody's above the mean, above the average, which always sounds like a good thing. It's not necessarily a good thing. I know I have a lot of runners in class. If you are above the average speed in a particular race, that's not necessarily a good thing. But in a lot of cases, above the mean would be good. A negative z-score would mean that you happen to be below the mean. Here's a quick example. If your height is 2 standard deviations above the mean, what is your z-score? That's exactly how we define z-score. Z-score is the number of standard deviations away from the mean you are. So if you're above the mean, your z-score would be positive 2. Okay, no calculations there. You don't necessarily need this formula here. We automatically know z is 2 if that's how many standard deviations above the mean we are. Let's say the next one we're going to need a little bit more calculating, though. It says if the mean shoe size is 9 with a standard deviation of 1, how many standard deviations away from the mean are you? If you have a shoe size of 7.5, what is your z-score? Keep in mind, the answers to those 2 questions are essentially the same. Okay, the number of standard deviations you are from the mean is whatever your z-score is. I'm hoping that before you do some calculating here, you're already thinking that since this is below the mean, your z-score should come out to be negative. So if I do the calculation according to this formula, the observed would be 7.5 minus the mean of 9. And then you actually just have to divide that by 1 for the standard deviation. Comes out to be negative 1.5. So when the z-score is a negative number, that represents how many standard deviations below the mean that particular shoe size happens to be. And we're going to start connecting all of this to different things like percentiles and things like that. That may not come up until tomorrow's lesson. But to go back to that example of standardized testing, when you get results back on a standardized test, like the SATs, which I believe some of you have taken, probably PSATs at this point. But if you've taken the SATs or the PSATs, if you get a score report back, typically you might get some information saying you scored in this percentile. And that has something to do with how many standard deviations away from the mean you are. Or maybe more commonly, if you've ever gone to the doctor and they said your height and weight are in a certain percentile, it's compared to people that are your age and your gender and how your height and weight relate to similarly grouped people of your age and gender. So we'll talk about that in coming up here. All right, we have an example at the top of the next page, example 3. We're going to talk specifically about femur length. I haven't taken bio in a while, but I feel like that's like the really big bone in your leg. You'll send me an email correcting me if I'm wrong. But femur length is normally distributed. The mean is 17.5 inches with a standard deviation of 1.3 inches. Calculate the z-score of the following femur lengths, round to the nearest hundredth. How do we calculate a z-score? You take the observed values in the 6 examples below, subtract the mean, and divide by that standard deviation of 1.3. So it's a pretty easy formula to use. I'm going to encourage you to hit pause real quick here, try those 6, calculate those z-scores, and then we'll kind of go on from there. Okay, so the first 3 examples, 18 inches, 15, and then 17.4. A length of 18 inches is going to be a positive z-score. It's going to be 0.38. Okay, so that's how many standard deviations above the mean that length femur is. Whereas 15 inches is pretty well below the mean in this case with a z-score of negative 1.92. Negative 0.08 would be the z-score if you're just 1/10 of an inch from the mean. Going on to the bottom row, if you are the mean, like we said, your z-score should be 0. Notice how when you're 1/10 of an inch bigger than the mean, that the z-score sort of matches this negative z-score up here. And that makes sense because those are equally spaced around the mean, so that you'll see that in any normal distribution. And finally, the last case, 20 inches, you get 1.92. So that 20 is the same distance away from 17.5 as the 15 inches was up here. Okay, so as a follow-up to that, what seems more likely to happen? A length of 20 inches or the length of 17.4 inches? So really just comparing these 2 cases over here. It really has nothing to do with which one's positive and which one's negative. It has more to do with, if we think about that normal distribution, which one's going to be closer to the center of that distribution where all that data is more closely grouped. So in other words, which one has a closer z-score to 0, or the mean and the averages? So it happens to be the 17.4 inches, much closer to 0 than 1.92 is. So 17.4, since the z-score is closer to 0, which indicates it's closer to the mean. And in a normal distribution, that's where most of the data is grouped. Okay. I realize probably as I'm talking through this that maybe it's a little bit fast. So you guys know the drill. Hit pause if you need to. Okay. There's 2 quick follow-up questions here at the bottom that relate to z-scores. So if you want to try them and then hit play, completely up to you. And then I'm actually just going to get you set up on homework 1, just because there's a little bit of calculator work to look at there. So example 4, given the average battery life of a AA battery is 21 hours, standard deviation is 2 hours. If the battery we tested has a z-score of negative 1.25, then without calculating battery life in hours, what does the negative z-score tell us first and foremost? So negative z-scores means that this battery life is definitely below the mean. So if the mean is 21 hours, I know that this particular battery lasted less than that. And then we can use our formula for calculating z-scores to determine how many hours the battery lasted. So the only thing that's a little bit different is we already know the z-score. So that's going to get plugged in on the left side of the equation. The value we're solving for is the observed, but we know the mean and we know the standard deviation. So you're just going to plug all that in. Here's our formula, observed minus mean over standard deviation. So if you plug in the z-score that we know, the mean, the standard deviation, however you best want to solve this, right? Maybe just multiply both sides by 2, add the 21 over. You're going to get that the observed value in this case is 18.5 hours. So I went really quickly through this lesson, like I was saying, but I think z-scores are going to be pretty easy for us to calculate. We're going to see a lot more of a connection in the next lesson with probabilities and percentages with these percentiles, like I had mentioned. So we'll see kind of where this relates and how we can make some more interpretations based on a z-score. Okay, the next page is just a little bit more practice. So again, I'm just going to show the answers. If you have questions about these, you'll let me know. But using that z-score formula, this is again in example 5, another one where you're given the z-score. You're going to be solving for the standard deviation, which is the value in the denominator. Okay, so the observed was 3 minus the average over the standard deviation. Okay, cross multiply, solve from there. Number 5, the standard deviation is 0.72. Example 6, just taking a look at another example we were given the z-score. This time I want to figure out the average. So the average in the formula is observed minus the average. So I put the x there over the standard deviation. Solve that for x. The average brake life in this car was 60,622.5 miles. Okay, and I really like the last example here because it's a good method of comparison here, especially since there are two very different, exams. If you get an 1140 on the SATs versus a 25 on the ACTs, how should you know which report you should really send to colleges? What's going to make you look better? Well, it sort of depends where those scores fall and how many standard deviations away from the mean they are in comparison to each test. So the mean and standard deviation for each of those tests is given, and we can use z-scores to compare and figure out which score we should send. So we've got the SAT and the ACT here. If you calculate the z-scores that correspond with the information, the z-score for your SATs was 1.4. The z-score for the ACT was only 0.875. So in this context, you can prove to the college that you performed a little bit better on the SATs than you did on the ACTs comparative to everyone else taking that test. So definitely send the SAT scores since it is more above the average than the ACT score would be. Okay, lots of good practice here. Like I was saying, I really want to wrap up quick here today by showing you how to type some data in the calculator, because that was not included in today's lesson. If you remember how to do this, you can probably hit stop on the video at this point and just try it on your own. And there are some good directions given to you anyway. But this data that we're looking at is it's 25 weeks of looking at how many miles per gallon you got in your car driving around from day to day. So it's a lot of data to look at here. But it says input these data into L1 on your graphing calculator. So it tells you how to get there, stat, edit, and then you'll see the first thing you'll do is hit enter for L1. But just as a quick reminder, if you hit stat, okay, right up here below delete, the first option is edit. So I'm going to hit enter for edit. I have already typed these data values in, so I'm not going to show you how to type each one in. But as you type in a data, you would hit enter each time. Let's say from all the way back in Algebra 1, you still have some old data stored in there, but you're like, I don't want these numbers, 1, 2, 3, 4, 5. If you go to the top of L2, I need you to hit clear and then scroll down and your list will be blank. Do not hit delete because that will delete the entire list from your calculator and you'll need to email me for instructions about how to get it back. Do not hit delete. So if you want to clear out a list like I just showed you, I don't want 1, 2, 3. You go up to highlight L2, hit clear, scroll down, it's gone. But anyway, I typed in all the data already. Once the data is entered, it says use 1var stats. So 1var stats is statistics concerning one variable. The only variable here is miles per gallon. Calculate the mean and standard deviation. And it shows you symbolically what the calculator defines those two things to be. So once you have your data entered, if you go to stat again, and then scroll one to the right and hit calc, the first option in calculate is 1var stats. So you'll notice that we already have our data typed into list 1. If you're panicking because you're saying, wait, Mr. All, my list 1 was deleted, I had to type it into list 2. If you hit second 2, and L2 will pop up. Second 3 would be L3 if we needed it. Okay. We don't have a frequency list, so you can ignore that. And then finally go down to calculate, hit enter. Okay, and then here's the information that we need. The X bar at the top is the mean for the set of data. So you're going to write that right here, 26.04. And then S sub X right there would be the standard deviation for the set of data. The standard deviation is 1.54 to the hundredths place. You'll see in other examples that we'll use the standard deviation right below it of 1.51. The difference between those two things is that this is called a sample standard deviation, S sub X. And since we have a sample we're looking at, that's why we're going to use that standard deviation. The one below it is called the population standard deviation, and that will be something that we probably use a little bit more frequently going forward. But in this specific example, use S sub X like it says to do on the homework. And that's pretty much it. I think the rest of the directions are pretty straightforward. I just wanted to show you that quick calculator work there. And of course, if you have any questions as you go along the way, let me know. But make sure that you stay tuned to some details that come up in some of the emails that I send, because there might be a few things that we wind up skipping and not completing within stats. So stay tuned for more info. Otherwise, I will chat with you guys soon.